Swayam Prabha. Digital India. Educated India.
So, in the previous class, we started our discussion on D-square law modeling for droplet evaporation. So, this model, as you can see, has been derived based on some set of assumptions. So, in this case, we basically solve the species conservation equation for the transport of the vapor. So, by solving this equation, we get basically the vapor mass flux at the surface of a droplet, an expression for that, which depends on the physical properties including the density and the diffusion coefficient of the mixture, and this transfer number Bm, which essentially refers to the gradient in the vapor concentration, which is responsible for the droplet evaporation process. This parameter diffusion coefficient is basically the binary diffusion coefficient, this. So, which means that here we are referring to diffusion of one gas into another. So, here in this example, it is the vapor of the droplet diffusing into air. So, this is known as binary diffusion coefficient. So, you can have, if you see in a strict sense, the vapor is diffusing into a mixture of gases, and the diffusion coefficient for each gas is actually different. What I mean is that the diffusivity of, let us say, water vapor into nitrogen is strictly not same as diffusivity of water vapor into hydrogen, but both are present. However, we are simplifying this and we are assuming that the vapor is diffusing into air only, where air itself is constitutes the another species, the second species. Okay. Then we could derive this expression which tells us that the rate of change of surface area of a droplet is basically a constant. So, that is the essence of this model, you can say. And from there we can calculate the vaporization time, and then we can account for the convective effect as well by incorporating another model where we account for the increase in the vaporization rate due to convection through this term that includes Sherwood number, which is analogous to Nusselt number in case of heat transfer. And finally, we could get an expression for the mass transfer rate or rate of change of mass of the particle. This is what is our final target. This is what we wanted to get. We wanted a model for this, for to close the mass conservation equation, and this is what we get. We can see an example of how do we measure K. So, this is a theoretical analysis that tells us that the rate of change of surface area is basically constant. But has this been experimentally validated? The answer is yes. So, since a long time people have conducted experiments using various type of liquids and to basically verify if the droplet evaporation follows D-square law or not. So, how do we measure this, the evaporation constant? So, when we say measurement of what? What we need finally is the evaporation constant. Okay, and then how do we get it? So, for that purpose, usually a droplet is suspended. Okay, in this case, it is suspended using a cross wire technique. So, there is a cross wire at the center of which you suspend a droplet. People have also used earlier a simple one fiber, a thin fiber, and hang a droplet. Then we can image how the droplet surface is changing with time. So, you take a series of photographs and from there you can calculate the how the diameter changes with time. Okay. Now, how do we get kV? So, we know that from d square law this expression is valid, and by integrating we get this, and by normalizing this with the initial droplet size or square of initial droplet size, we get this expression. So, now if we plot the ratio of the normalized droplet surface area with respect to this parameter, then the slope should be equal to the vaporization constant, and that is what is done here. So, here I am giving two examples. One is a heptane droplet and the other one is an ethanol droplet. So, we hang this droplet individually like this, and this has been photographed, or the vaporization process has been visualized using a high speed camera, and using image processing technique we can calculate the size of the particle at different instant of time, and if we plot the normalized surface area, then you see that it indeed follows a linear trend, and the slope is nothing but the vaporization constant here, the evaporation constant. Okay. And now, you see that the slope is different between heptane and ethanol. So, from here we can try to understand what causes this difference. This difference is basically due to the difference in the liquid density, vapor density, which is not much different. Actually, this density corresponds to the mixture density of the mixture, but it is usually taken as the density of air. Okay. Then this is the diffusion coefficient. So, we need to look at these individual properties for the two liquids separately. Okay. And then here we have the transfer number, which essentially depends on the difference in the vapor concentration at the droplet surface and far away from a droplet. So, in this particular cases where we consider heptane and ethanol, this term we can assume it to be 0, because there is no vapor of these fuels present in air usually. Okay. So, now you need to know what is this, and we will discuss this how to obtain this one, but it depends on the temperature of the droplet. But from the experiment you get kV, and using this expression we can explain why the value of kV is higher in one case compared to this. So, in these two, which one evaporates faster, or which one has higher evaporation constant, in which case slope is higher for heptane. So, in a given time you see that the change in droplet size is higher. Okay. So, higher the slope, higher is the evaporation rate basically. However, the d square law may not be strictly valid, also this we will see sometime later, for all liquids, because some other factors come into picture which was assumed not to be present in case of d square law model. For example, we have assumed that the liquid is monocomponent. Okay, that assumption is inherently there, but if it is not, then for example, if I mix heptane and ethanol, then the question is, still should we have a similar plot? Okay. So, so there can be deviation depending on the liquid that we are considering. Okay. Now, we will move on to derive the same model but using energy approach. So till now what we considered, we considered only the species transport, or we derived the model based on mass transfer analysis. Now we can derive the same model using heat transfer analysis, and why this is required you will see soon. So in this case, here we assume that the ambient temperature is more than the more than the temperature of the droplet, though this is not a restriction. Okay, so for understanding I am assuming this. So in this case what happens, that the heat is transferred into the droplet from the surrounding. Okay, so now we can define the heat flux as QR at any radius r. This is similar to the mass flux, vapor mass flux which we derived. The analysis is quite analogous, as you will see, and Q naught is the heat flux at the droplet surface. So now if we use energy conservation equation, what we get is that the total flow of heat, or the heat flow rate, is basically constant. Why it is constant? Because there is no external source of heat generation or dissipation. Okay, so basically the heat flux times the surface area is constant, and accordingly we get this expression, that the heat transfer rate at any radius is equal to heat transfer to the droplet at the droplet surface. Now again, this heat flux that you see, it has two parts. One is the convective flux, one is the diffusive flux, as in the case of mass flux. So this is the convective flux part and this is the diffusive flux part. Okay, so now if you see, what is alpha here? Alpha is a thermal diffusivity, rho k lambda by, or thermal conductivity by rho Cp. Here what you get is minus, which refers to the heat flux, conduction heat flux or diffusive heat flux. Okay. So then now this is equal to this term at the surface, where Q naught represents the diffusive heat flux at the droplet surface. Okay, so we can do a similar analysis as we did earlier, and here we remove the bracket, and again from mass conservation this term is equal to G naught R naught square, and we can club all terms with radius and all terms with temperature, so that we can we can solve this equation through variable separation method as we did earlier. So now you integrate, and then the integration is from T naught to T infinity now. Okay, and then we get an expression which is very similar to what we got earlier. So here we see that the vaporization mass flux is equal to rho times alpha. Earlier here we had the diffusivity, mass diffusivity. Here we have thermal diffusivity divided by R naught ln 1 plus Cp times T infinity minus T naught divided by this term here. Okay, and this is nothing but thermal transfer number. So earlier we had mass transfer number, here we have thermal transfer number. So according to energy transfer analysis, the process that drives the evaporation process is basically temperature gradient. Earlier it was the gradient in the vapor mass fraction, and now it is temperature gradient. Okay, and now if we do an energy balance at the droplet surface, what do we get? Let's see. So the term on left side represents the heat transfer rate to the droplet. So this is the diffusive heat flux times the surface area. And why it's a negative sign? So, if you see in this case, we have heat which is diffusing into the droplet. So, this is the radial outward direction and this is Q naught. Okay. So, that is why their product is negative. So, basically the dot product of the heat flux which is inward, radially inward direction, and the area vector which is radially outward direction is negative. So, that is why we have put minus sign to show that the left side is positive in this case, that is heat is transferred to the droplet, and that is equal to the rate of change of internal energy of the droplet, which is nothing but d by dt of mCt, okay, plus the heat loss due to evaporation. So, this tells us that out of the total heat that the droplet receives, part of the heat is used to rise its temperature and the other part is used to evaporate the droplet. So, simple energy balance, that is what we are getting, but this equation is very important. Okay. So, now if you consider, let us say you have a heated droplet in ambient condition. Let us say initial temperature of the droplet is say 60 degree and you have the droplet in room condition, then what will happen? This term will be, the term on left side will be negative, because in that case the heat will be transferred in the outward direction only, because the droplet will try to cool off, okay. And this term, if you see this one, this is always positive, because G naught, this is G naught. So, G naught times area is always positive. So, we can show that the rate of change of energy of the droplet in that case where we have a heated droplet evaporating is always negative. Are you getting it? And it is negative because the droplet is losing heat due to the temperature gradient as well as losing heat due to the evaporation process. So, that is why this expression is a general expression. Okay. Now, at this moment, so we can assume that the rate of change of size of the droplet, okay, is much lower than or smaller than the rate of change of droplet temperature. So, here we are making an assumption. Okay. So, what will happen in that case, that the droplet size is changing very slowly compared to the rate of change of energy of the droplet. So, we can treat this R naught as constant, okay, and take this part out, and then we will get this as rate of change of temperature only with this assumption, okay. And then we can further simplify this to calculate the rate of change of temperature of the droplet in terms of Q naught and G naught. Okay. Now, when this will happen? We have this term. So, this represents basically the evaporative flux, or how fast the droplet evaporates. Then we have thermal diffusivity of the liquid, how fast heat diffuses in the liquid. So, if the heat diffuses in the liquid very fast and its droplet temperature is always constant in that case, okay, then we can have a scenario where this is valid. I hope you get it. So, see, this means that the droplet size is changing, okay, and heat is diffusing. Now, if the heat diffusion is much faster compared to the rate at which the size changes, then we can make this assumption, and we can define a non-dimensional number called Packlet number based on the comparison of the evaporation constant to the thermal diffusivity of the liquid. Okay. Anyway, here the point is we are making this assumption and we get this expression. So, the point here is that even if we are making a steady state analysis, we are able to get an expression for rate of change of droplet temperature. So, that is the bottom line here. Okay. Now, here the concept of equilibrium vaporization comes into picture, which is very important. So, equilibrium vaporization means this is a scenario such that the heat transfer to droplet surface is just sufficient to vaporize the liquid by providing the latent heat. So, in that case, what will happen is that the rate of change of temperature is 0, and the heat that, and temperature is independent of time, and the heat that we supply is basically used to evaporate only. So, this can be seen or visualized through this simple example. Now, let us say I introduce a droplet which is at 25 degrees centigrade, and let us say the surrounding temperature is 200 degrees centigrade. Okay. So, now if I plot temperature of the droplet with time, what kind of trend you expect? What will happen to droplet temperature? So, at time t is equal to 0, you suddenly introduced this droplet which is at 25 degree into an ambience of 200 degree. Then what will happen to the droplet temperature? It will increase, but during that time, okay, let us see. So, first it increases, then what will happen? Should it go on increasing? When? When it will be constant? Equilibrium means what? In case of, let us say you have water droplet, then at what temperature the temperature won't rise further? Boiling point. So, if assuming that you are having 1 atmospheric pressure, then the temperature will remain constant. So, this part refers to basically the equilibrium vaporization region. So, when you have this, then the heat which is transferred to the droplet is only used to vaporize, and this part is known as this part, droplet heat up period. Using this analysis, we can now calculate how long it will take for a droplet to have droplet heat up period. Okay. Now, this can be important in different applications. For example, again, if you consider a petrol engine, so there we introduce a mixture of fuel and air. Okay, in case of petrol engine, the droplets might not be there, it might have evaporated already, but if you consider, let us say, diesel engine. In case of diesel engine, we inject when the piston is at the or close to the top dead center, right. So, then what we want the droplets to do is that we want the droplets first to evaporate, mix with air, such that auto ignition can take place in case of diesel engine. Okay. But by that time the piston is also moving. So, this evaporation process has to be fast, otherwise the droplets would go and hit the top part of the piston. Now, the evaporation rate will obviously be faster when you have equilibrium vaporization. So, now how long it takes the droplet to heat up to the saturation temperature. So, this time is important. Okay. Okay. So, now you understand what is meant by equilibrium vaporization. Okay. So, now if we summarize, so we did mass transfer analysis to get the expression for the vaporization flux, and this depends on the mass transfer number, which depends on the vapor mass fraction at the droplet surface, which essentially depend on the temperature of the droplet. But the question is, do you know the temperature of the droplet? Do we have this information? Now let us start with a very simple case. Let us say I just hang one droplet here in this room, which is maintained at 25 degree. Do you expect the droplet to evaporate? After, let us say you come after 1 day, will you see the droplet? No, answer is no. So, this means that evaporation is taking place. Now, if evaporation is taking place, what would be the temperature of the droplet? Can it be 25 degree? So, if you argue that yes, it is 25 degree. So, if both the ambience and the droplet are at 25 degree, can evaporation take place? How heat transfer will happen? See, for evaporation to occur, heat has to be transferred from ambience to the droplet, right? So, without a temperature gradient, how can you have heat transfer and evaporation? So, in this case, the droplet temperature will be less than, or it has to be less than the surrounding temperature. Okay? And this is closely related to the concept of wet bulb temperature. Okay? Now, from heat transfer analysis also we get similar expression. Okay. Now, but both of the expressions must be same, right? Whether you do heat transfer analysis or mass transfer analysis, the expression for the vaporization flux at the surface of the droplet must be same. So, by equating this, we get this expression where this parameter Le is known as the Lewis number. So, here we have this Lewis number, which is the ratio of the thermal diffusivity to mass diffusivity. So, if you see, we have three type of diffusivity: mass diffusivity, momentum diffusivity, then thermal diffusivity, and accordingly we have three numbers which compare these three. Okay. So, first Prandtl number nu by alpha, then Schmidt number that we discussed in the previous class, alpha by d, and now we have Lewis number. This is Schmidt number is nu by d, Lewis number is alpha by d. Now, okay. So, now if we assume that Lewis number is nearly equal to 1, which is mostly the case, which is of the order of 1 at least, then or thermal diffusivity and mass diffusivity are same, then we must have Bm is equal to Bt. So, here also you see, if alpha is equal to d, then the expressions are just same. Okay. And then we get this expression Bm is equal to Bt. But the question is again, do we know either Y0 or T0? To calculate Y0, you need T0, but you do not know T0 also, as we just discussed. So, then what to do? We need another equation. So, we have now, if you equate Bm to Bt, you will get one equation, but you have two variables. So, you need another equation to solve it. And if we assume equilibrium vaporization, that is the heat flux is basically equal to the latent heat times the vaporization flux, and Bm is equal to Bt, then we get this equation. But we have we need another equation, that is Clausius-Clapeyron equation, that relates the vapor mass fraction to temperature. How? This way. So, this is your Clausius equation, Clausius-Clapeyron equation. So, basically this equation gives you the saturation pressure at any given temperature. So, here we are always assuming that the vapor close to the droplet surface is saturated. So, what we need is saturation vapor mass fraction. Okay. Now, for that we need to know what is the saturation pressure itself, and that we get through Clausius equation. Okay. Here the P reference, T reference refer to some reference condition. Again, in this example of a water droplet evaporating under ambient condition, we can take P reference, T reference corresponding to the ambient condition of 1 bar 25 degree. So, from there you get the P naught. Then we can calculate the mole fraction as the saturation pressure divided by the total pressure, and in this case total pressure is ambient pressure. So, you get mole fraction. Once you get mole fraction, you can get the mass fraction. Okay. And then we have to solve these two equations simultaneously to get Y naught and T naught. So, how do we do that? So, you initially assume some temperature and then calculate this, calculate left side, right side, see if they are matching, otherwise iterate. Okay. So, through this process we can now get what is Y naught and T naught. However, there are some scenarios where we do not have to go through this entire process, it can be simplified. An example is this, that if the ambient temperature is much lower than the boiling point, for example, what we just discussed, water droplet evaporating under ambient condition. So, in that case, yes, T naught has to be less than T infinity, but it will be very close to T infinity. So, it is safe to assume that T naught is equal to T infinity. So, you put T naught is equal to T infinity and calculate Y naught directly from Clausius equation and calculate Bm or the mass transfer number. You do not have to go through this entire route. Okay. Another example is if the ambient temperature is much higher than the boiling point temperature, in that case the temperature at the droplet surface will be close to the boiling point, but it will not be equal to the boiling point. Okay. So, in that case we can assume T naught is equal to the boiling point itself and use Bt or the thermal transfer number to directly calculate the Bt value instead of going through this route. However, if T infinity and the boiling point temperature are comparable, we have to solve both equations. Let us do an example problem, then it will be more clear to you the concept that we are discussing. So, let us say you have a water droplet, let us say 100 micron droplet with initial temperature of 25 degree, which is introduced into stagnant air ambience maintained at 1 bar 200 degree. Now, calculate the droplet vaporization time. First, by assuming equilibrium vaporization, and second by accounting for droplet heat up period. I hope the question is clear to you. So, the droplet with initial temperature equal to 25 degree is suddenly exposed to a ambient which is at a temperature much higher than the boiling point of the droplet. Okay. Now, calculate the droplet evaporation time by assuming equilibrium vaporization means you always have the equilibrium temperature right from the beginning and then account for the heat up period and then calculate the vaporization time and compare them to see how important is heat up period? If I assume, so in other words, if I assume that the heat up period is absent, okay, how much error can we introduce? So how to approach this problem first of all? What do you think? So first we consider the first case where we have equilibrium vaporization, and as I said, because the ambient temperature is much higher than the boiling point, then we can assume T naught is equal to the boiling point itself, and we calculate the thermal transfer number. Once you know thermal transfer number, you can calculate the evaporation constant. Once you calculate evaporation constant, the time of evaporation is nothing but d naught square, or the initial size, divided by the evaporation constant. So it is straightforward, and it was possible because we made two assumptions. So what are the two assumptions? First one is this, that you have equilibrium vaporization. Second one is this. Okay. Now, another practical problem. How will you evaluate the thermophysical properties? At what temperature? We can evaluate the properties at some average temperature. Okay. So we can calculate the average temperature this way, though sometime we do a weighted average also. Okay. And we need to evaluate the latent heat and the density at 1 bar and at the boiling point of the liquid. Okay. So once you know these properties, then the calculation is straightforward. Okay. So you should do the calculation by yourself. But let me add one more problem that you should also solve. Now, in this case, you remove this assumption. Okay. Assume that you have equilibrium vaporization only. But if you don't assume this, then what should we do? We should solve both equations and see what is the actual temperature. So I want you to calculate that also and see how far this assumption is valid. So is our droplet temperature actually close to the boiling point or not? Okay, that you can calculate by solving the two equations. Okay, so any queries as of now? Okay, now let's go to the next part, that is, how do we account for the droplet heat up period? Okay, so now this requires some calculation, as we will see, and it is quite interesting also. So first, what is given is your the temperature. So now you need to know how this temperature changes with time. The expression that I just gave before few slides, the rate of change of temperature itself depends on Q naught and G naught. So you need to evaluate these two, and that is what we will do. So in this case, you can start with this, and then using Clausius-Clapeyron equation, because you know T naught, so you can calculate what is the vapor mass fraction at the surface, and with that you can calculate what is Y naught, that is the vapor mass fraction at the surface, and then you can calculate the mass transfer number Bm, and from there the G naught, and you get G naught, and then we know this relation between G naught and rate of change of size. How? If you remember, we can express the rate of change of mass through G naught. G naught time the surface area is basically rate of change of mass, but this is also equal to rate of change of density times the volume, and by equating these two we got this expression. So if we not, the point is that if we know what is G naught, we can calculate what is the rate of change of particle size. Okay. But if we know G naught, we can also calculate what is Q naught. So if you remember, we had derived an expression based on the, we started from energy conservation equation and then we derived an expression for G naught. You remember? So from that expression only, from that I can calculate what is Q naught when G naught is given, and all other parameters are known. Okay. Then once we know Q naught, then you can calculate the rate of change of temperature of the droplet using this expression. Okay. Here what was the assumption? That the rate of change of particle size is much slower than the rate of change of particle temperature. So once you know what is the rate of change of particle temperature, you can recalculate in the next time, you can recalculate how the temperature has changed. So let us say you start with 25. So next time it may become, so depending on what is the time step that you are choosing, you can update the value of T naught. But in the meantime, do you update the particle size also? The answer is yes, because the droplet is shrinking now. So you can update the particle size here before you calculate the G naught. Okay. And you continue this till your particle size is close to 0. Okay. So this is how it has to be done. So you need, obviously you need a code to for this calculation purpose, but it is not difficult, you can do it. Okay. And then you can see how long it takes actually the droplet to evaporate. In fact, it will be interesting if you plot temperature versus T naught or rate of change of the particle size and see what trend you are getting, and this should give you the droplet heat up time.